And all right.
Folks are going to continue to trickle in likely over the next few minutes, but I
Okay.
will just go ahead and get us started here. So, good afternoon or good day, depending on where you are in the world, where you're joining us from. So, my name is Val Schwartz. Most of you know me. I'm the head of admissions here at NC State's Institute for Advanced Analytics, and welcome to our Exploring Data Science webinar series. So, this today is actually the final installment for this academic year. And today we'll be learning about the statistical technique of multi-level modeling from Dr. Paul Dennis. So Paul holds bachelor's, master's, and doctoral degrees in psychology, and he completed the Master of Science in Analytics program here at NC State last year. And in addition to teaching at Duke University School of Medicine, he serves as a faculty statistician for the Durham Veterans Affairs Medical Center. And with that, I'm going to turn it over to Paul. I'm going to also hit paste in the chat. I'm going to share with you what I've shared with just about everybody previously, which are some resources that Paul provided to accompany his talk today. And he said that he's not going to be looking at the chat while he's presenting, but if you have questions, feel free to just unmute yourself and interrupt him. And he said he's perfectly fine with that. So Paul, the floor is yours.
All right. Well, thanks so much, Valerie. Thank you for that introduction. I guess I don't really have to introduce myself now. It looks like an intimate session. So yeah, I definitely urge you to interrupt me with questions. And if it gets out of hand, then I may just say like, okay, we're going to kick some of these to the end of the presentation. But this looks like a nice small group, and I think we'll probably benefit if I can address questions on the fly. So today I'm going to give you the quick and dirty on multi-level modeling, or MLM, which is a statistical technique for analyzing hierarchically organized or clustered data. And Valerie already put this in the chat, so this is kind of a moot point, but of course, there are going to be some lecture materials, there are going to be some other resources that are pertinent for using multi-level modeling. And of course, I have a SAS data set and a syntax file in there, which I'm going to pull up and use today during the lecture. And after the presentation, I'll post the PowerPoint up there as well. So I'm going to start with this quotation. I really like it. I hope it will foreshadow how life-altering this presentation will be. If not the presentation, then at least the procedure. So this may sound like something from an undergraduate course in political philosophy, but these are actually two statisticians out of UCLA. And of course, they're referring to multi-level data. Now, multi-level modeling is a technique that was developed back in the 1990s, which I kind of dismayingly recognize is before your time. I learned MLM back during my first iteration in grad school 10 years back. I had a semester-long course in it. And honestly, much of my career can be attributed to my application of this technique, because as this quote suggests, once you're aware of hierarchies in data, you really can't unsee them. So MLM goes by several different names, some of which you may have heard of, probably most not. It's commonly referred to as hierarchical linear modeling, mixed effects modeling, which refers to mixed fixed and random effects modeling, and it includes special cases of analyses such as cross-classified modeling, and it can be applied to growth curve analysis. I'm simply going to refer to this broad set of analyses as MLM. And the advantage of MLM is that it addresses a key shortcoming of ordinary least squares regression and other generalized linear models, including logistic regression. So as you're aware, there are a number of key assumptions underlying ordinary least squares regression and logistic regression. For instance, there's the assumption that there's a linear association between predictor variables and the outcome variable, or the logit of the outcome variable in the case of logistic regression. Now, homoscedasticity is assumed in linear regression, as is the normality of residuals. And of course, probably the most important assumption of both linear and logistic regressions is that the observations are independent from one another. So as that quotation from a couple of slides before suggests, there are many scenarios, arguably most scenarios, when that is not the case. So say you work for some capitalist institution, and I'm going to be vague because I work in government, And you want to know whether a promotion is leading to greater customer utilization of some product. Well, if this is a national or regional promotion, you probably have more than one branch or more than one store. Do you want to assume that that promotion has the same effect on all customers across all locations? And is it even safe to assume that? That's where MLM comes in. So here are a few other scenarios in which MLM could be applied. So similar to that last example, you may have bank customers nested within local branches. You can have patient outcomes clustered within physicians, or it could be medical centers or hospitals. You can have employees nested within teams or organizations. Now, these first three examples all feature individuals clustered within larger structures, but you can also model occasions within individuals. For instance, match performances clustered within an athlete, or end of grade test results nested within students. Now, this is how I came to learn MLM, because as a developmental psychologist, I was interested in how individuals change over time. So this is a great way for handling repeated measures data. So for this class, I'm going to use some data from a study that I worked on a few years back. And this is not the actual data set that you're going to find in that Google Drive folder. I jiggered some of the variable values so that they're essentially simulated. That way I can avoid violating data use agreements. To give you a little background, one of the aims of the study was to examine how PTSD, or post-traumatic stress disorder, and related symptoms like depression, isolation, hostility, and aggression are associated with health conditions like poor sleep, high blood pressure, and insulin resistance. So in this study, participants were brought into the lab at baseline and completed a battery of surveys and clinical interviews. They were then fitted with ambulatory electrocardiogram monitors. And these are basically patches that collect information on heart activity that are then read in by a watch. These captured indices of autonomic nervous system functioning. So basically fight or flight, arousal in response to some kind of excitation, and then the recovery or return to baseline following that arousal. So in tandem with the physiological monitoring, participants were given smartphones that were programmed with electronic diaries. So every few hours, an alarm went off and they were prompted to answer questions about their current activity level, where they were, what their current mood was like, and other environmental features. So here we have clustered data because we have mood and indicators of autonomic nervous system arousal nested within individuals. So here's the actual data that we're going to be using today, and I'll run through the variables really quick. The ID variable is a unique identifier for each person in the data set. So you'll see that person 5 here has numerous lines. Each line represents a diary entry. Age is a person level variable representing age in years at baseline. So you can see that that's invariant within an ID level. We also have waist hip, which is another person level variable representing waist hip ratio. You can think of this as an alternative to BMI. DTS is a self-report scale. It captures PTSD symptom severity. It stands for the Davidson Trauma Scale, if you're interested. And scores can range from 0 to 136, with higher scores representing greater symptom severity. And activity comes from the electronic diary and represents participants' activity level at the time leading up to that diary entry. So 1 represents running, 2 walking, 3 standing, and then 4 sitting or lying down. So higher up on that scale means lower activity level. Neg-AF is the average of 7 self-report questions, capturing essentially how negative participants were feeling at that moment on a range from 0, meaning very little, to 10, reflecting a lot. And then finally, we have the biosensor data. So HR30 represents participants' average heart rate in the 30 minutes overlapping that diary entry. LF30 is a measure of heart rate variability, what's called HRV. And HRV is inversely related to heart rate. So it basically captures the nervous system's ability to recover from excitation. So again, it's inversely related to heart rate. When heart rate is high, HRV is low. And FF30 is another measure. So LF stands for low frequency, HF is high frequency. They're just different ways of measuring heart rate variability. So are there any questions about this data set structure and what you're seeing here?
Hey, Paul, I have a question. Um, Great to see you also, by the way. So for this data set in particular, you're looking at a lot of different, like, so say it's like the same patient, but also looking at multiple rows of the same activity. So like 1, 2, there are multiple rows of like activity 2 and 3 here. Would the same, you'd still be able to do the same thing if there was only one activity per patient here?
If there was only one activity per patient, then that would be treated very much like age or waist hip ratio in this case. So it'd be invariant within each person.
Okay.
And so we're going to see in a moment how those different variables are modeled. So variables that are invariant within people and variables that do vary within people. And it's great to see you too. I wish I could stop the presentation momentarily to catch up with you, but it's wonderful to see you.
Yeah,
And great question.
Awesome. Thanks.
Does that answer it for you?
Yeah.
All right. So we will get back to the data shortly when we go to SAS. So a couple things about the data structure. As I mentioned before, the data are organized in a tall format such that each row represents a time point for a specific person. So with this structure, multi-level models use all available rows of non-missing data. So this is what is referred to as row-wise deletion, as opposed to case-wise deletion. Case-wise would be the scenario in which we are missing some occasion for a person, and we end up removing that entire person and all their observations from the analysis. So if we are running, trying to run a similar analysis with repeated measures of ANOVA, which you may be familiar with, that's a case when you lose someone, an entire person, if they're missing any data. So because MLM can model all available data, it can accommodate 2 types of missing data. For one, it can accommodate data that are missing completely at random. And this is a fairly straightforward scenario. It's basically the same for any single level analysis like ordinary least squares regression or logistic regression. So if the missingness really is random, your estimates are going to be unbiased. So your model is safe. There's a second scenario in which data are considered missing at random, so not missing completely at random. And this is a little different. So you know that your data are missing at random if you can predict that missingness with the data that you have. For instance, say you get a political survey in the mail and you're feeling really politically engaged, so you plan to fill it out. And you respond to the questionnaire, you say, yep, this is how confident I am I'm going to vote for this person. And then you get to a bunch of sensitive background questions. How much is your income? What's your education level? Do you go to church? And you start to get cold feet and you say, you know what? I'm not gonna fill this in. I don't want anyone knowing that stuff. Now, in this case, missingness is not associated with the outcome and only the outcome. It's more attributable to the fact that you don't want to provide your income or your education or your religious affiliation. So in this case, a reliable model can still be constructed to estimate the relationship between these background variables and candidate perception. In other words, that association between the background questions and candidate perception is unrelated to missingness. It doesn't matter whether or not the data are missing. You can still derive the same relationship. But what happens if the missingness is primarily related to the outcome variable? And this is something that we see a lot in clinical studies where, for instance, participants may be enrolled in a lengthy trial that has them reporting to a clinic once a week for 6 weeks. So pretty big commitment. Now, once they stop seeing improvements, these patients often say, you know what, forget this. I'm not going back there. And they drop out. So when this happens, the outcome data are missing. Now, if we actually had access to those data, we could see that improvement had stopped for those folks, and that people who come in, they continue to see improvements by and large because they're still committed to the treatment. But if we rely solely on the available data, we'll get this inflated sense of the treatment efficacy because everyone who's coming back is improving, and we're not seeing the people who are not improving. So this is what's called data not missing at random. And so when we approach a data set, we have to be kind of keenly aware, what are the reasons why we're missing data? And again, it's okay if your data are missing completely at random, or even if you can predict missingness. But if you have reason to believe that your data are not missing at random, you will get biased results from an analysis. And that's not just multi-level modeling, that's really any analysis. So that's something to be keenly aware of. Okay, so I should probably ask if there are any questions there. I'm going to assume that you don't have any because that's kind of a tricky subject and there's a lot of literature on it. So if you want a better foundation, feel free to dive into that. But Rohan, do you have a question?
Yes, and I know I understand how like tricky tackling missingness is. So I was just kind of wondering, like, just more so in practice, is it ever used with like mixed effects modeling? Is it ever used like as a fail-safe system when you're collecting data as you go to kind of anticipate missingness and mitigate it? That because right, you're not going to lose your entire experimental unit, but you know, you might lose some granularity. Is that ever a practice, and is that a good practice to have?
Well, in clinical studies, there are missing data approaches that we use. So particularly the most conservative approach to use is what's called intent to treat, where you say, I am going to model everyone that's enrolled in my study as if they received the full treatment. So even if they drop out, they're going to get included in the analysis. And what I'm going to do is I'm going to impute a value for them. And it's considered conservative because the value that you impute is basically that there's no improvement in their outcome measure. That
right,
if they're not receiving the treatment,
hoping for.
so that's very conservative. I mean, there's certainly scenarios in which you can make the argument that, you know, these data are missing at random. You know, we think that if we can model, we have a lot of background or baseline information on what's missing. And so we can model, we can see like, yeah, you know, older people may have a harder time coming in, or people who live farther away from the clinic have harder time coming in. We're going to include those folks in the model. So we do have people who live farther away and we still have outcome data. And the reason why this is robust is because that data, even if you have some data on folks who are missing, or some data on folks who are similar in missing, what you can do is you can extrapolate, but this is what the model does. It extrapolates from the data that you have. So if you have at least even just some people, if maybe a quarter of the people who live, you know, 100 miles away from the clinic, even if a quarter of them come in versus 75% of people who live closer than 100 miles, the model is still going to be pretty robust with the data that you have available. The problem is if that outcome data that you're missing could likely be due to differences in the outcome level. It's like, oh, they're not seeing a treatment, they're not coming back. That's where you come into
Right.
problems. And that's where you have to, it's good to have some kind of strategy for how you're going to handle those missing data, like intent to treat in clinical studies.
Right. Makes sense. Thanks.
Yeah. And I'll also note that there are some techniques, there's some pretty robust deep learning techniques for imputing missing data. So before I went to the Institute, the most common technique to use was called multiple imputation. So basically you take a correlation matrix of all the variables, and you take that correlation matrix, and for values that you're missing, you impute. So it's basically like you're simulating data for missing values. And you create a bunch of data sets drawing from these simulations. So of course, simulation is based on parametric assumptions. So you end up with a bunch of imputation data sets where you've imputed missing values based on the covariances between all the study variables. And then you run your model and you average all the effect across those imputed data sets. Now there are more sophisticated techniques that use like random forests and deep learning. And some of these are actually robust to not missing at random data. So I think data wig is one you might want to look into if you're interested in this. It's just data wig, WIG. I recently read about it. It's a Python package in case you're interested. So wow, just went down a big tangent.
No,
Okay.
no, absolutely, absolutely. I really appreciate it.
Yeah, sure thing. So before let's go back. So we've already seen the data set. We're going to start building a model. And so let's say that we want to model low frequency HRV. And remember, this refers to the nervous system's engagement in restoring your body to baseline after excitation. So the inverse of heart rate. And our basic hypothesis is that negative affect is going to be negatively related to low frequency HRV, because when you're experiencing a lot of negative affect, that's a type of arousal. And so your nervous system is not restoring itself to baseline. So hopefully that's something you can follow. So when we begin modeling multi-level data, you start out with a null model. And the reason for this is to partition the variance in your outcome variable. That is, you want to ascertain how much variance in your outcome is due to differences between your clusters versus differences within your clusters. In this case, our clusters are individuals. So in other words, we want to know how much variance in these LF readings is due to between person differences versus within person variability. So the basic equation for our null model differentiates between the levels of the analyses. At level 1, in this case, we have 30-minute low frequency HRV readings for person I at time point T. That's what those two subscripts mean. So in the null model, the only effect that we're going to model is the intercept. And here the intercept has a subscript of I. The intercept is beta naught. And that tells us that each person in our data set will have their own intercept, meaning their own average value of low frequency HRV. Now, of course, we're modeling multiple LFs for each person. So there is a residual error corresponding to each individual I and time point T. So does that first line of this equation make sense? You can chime in if it doesn't, otherwise I'll keep going. All right, great. So we can take those intercepts, remember, one for each person in our data set, and further indicate that these can be represented by a grand intercept. So basically the sample mean of LF plus a person-specific deviation from that grand intercept. Okay. I know that gets a little more complicated, so stop me if anyone has any questions about those two pieces of this equation. So level 1 is at the level of low frequency readings. Level 2 is at the level of each individual in the model. So that's what makes it a multi-level model. Through substitution, we end up with this simple formula. The value of LF for a given person at a given time point is equal to the grand intercept, or basically the sample mean of LF, plus a person-specific offset, plus a time point specific offset for each person. Now we refer to this grand intercept as a fixed effect because it's the same or fixed across all participants. And these error terms are considered random because they vary across the participants. Moreover, they vary in some way that we aren't fully explaining or modeling. So that's why it's called a mixed fixed and random effects model. Any questions about that? This is all, I know my eyes tend to go blurry when I see equations, so I understand. Feel free to chime in if you have any questions. Okay, so we are going to next look at the SAS code that we're going to use to run this null model. So this is proc mix. This is for modeling linear mixed models. There is a proc for modeling nonlinear models. I listed that and a fairly lengthy appendix with a number of other topics. And maybe we'll cover some of that depending on how this goes. So the main things that you need to know is that the null model will look just like your model with predictors, except that it's empty on the right side of that equal sign. The /s tells SAS to give us regression-like coefficients, because otherwise SAS by default will only provide type 3 ANOVA-like output, so f-tests rather than t-tests. The DDFM portion tells SAS to determine denominator degrees of freedom using the between within method. So this is a very efficient method, and it's appropriate when the number of clusters that you're analyzing is fairly high. I tend to use it by default because this is what I was taught. You should know there are other options. It kind of depends on the industry, which options are most typically used. These options will have typically subtle effects on your results because, again, these are degrees of freedom, so those will influence your standard errors and ultimately whether or not your effects are significant in the model. The covariance structure refers to what kind of assumptions you wish to make regarding how observations may be related to one another. Now, by specifying type equals un for unstructured, I'm telling SAS that I don't wish to make any particularly explicit assumptions about those relationships. In fact, I want SAS to estimate those directly from the data. Now, this is not a particularly efficient method. There are other methods where you're making assumptions about the structure of the data. And I've included documentation on that Google Drive that provides some explanation for these various structures. But again, type equals un means that you're not making any assumptions. So it's kind of a safe bet to use. So now we're going to go to the SAS code. See if I can pull it up here. And we're going to run this null model. So at this point, hopefully all of you have access to the data, but you can certainly just follow along with what I'm doing. So I just read in the data set, which you'll see here. We already took a look at it. Here we have ID, age, waist tip, et cetera. And then over here is where we have variables that vary within the person. So level 1 variables, and then these are considered level 2 variables. So here's our null model. Again, it's empty on this equal sign. All we're going to get is an intercept. So when we look at the output, as always, SAS provides you with a lot of different information. Most of it you won't need. It's going to tell you what you're modeling, what kind of covariance structure you're using, what is your identifier for your various cluster levels. It'll tell you how many different cluster levels you have, or how many different clusters you have, and then the various identifiers for those different clusters. Max observations per person is 51. If we scroll down, we'll see, scroll down a little bit right here. This is where we really get into the information that we want to draw from this null model. This output table here called covariance parameter estimates, these are the variances for our random effects. So again, the random effects capture between person differences versus within person variability. So this top line that says subject ID, that's telling us the variance estimate for between person differences. These are between person differences. This is telling us within person variability. You'll see that both of these are significant. So we have significant variance at the between person level and significant variance at the within person level. Typically, that's what you'd expect with a multi-level model, because why else would you run a multi-level model if you don't have significant variance? There are occasions when you may do that, but usually that's driven by theory. And it's not likely that you'll encounter that. So we have one effect that we modeled, and that's the intercept. Now, SAS by default will just give you grand estimates, which that means is the sample estimate for the intercept. So in this case, we have no other effect. So this is the sample mean for LF. You can request, because again, when you look at our equation, we're modeling intercepts for each person in our data set. SAS will provide that, but you have to add additional code, and it's not necessarily typical that you would request that information. SAS doesn't provide it by default, but a simple ODS statement may provide that for you. Now that we have that, I'm going to go back to our PowerPoint, because this is where we can partition our variance. And we partition the variance by calculating what's known as the intraclass correlation. So quite simply, the total variance in LF is composed of two pieces, the level 1 error variance plus the level 2 error variance. So level 1 referring to within person variability, level 2 referring to between person differences. So the ICC is simply the level 2 error variance divided by the total variance. Thus, it captures the proportion of variance and the outcome variable attributable to between person differences. Does that make sense? It's just a simple ratio. We can add those variances together to get the total variance in our model. And because we partition those variances, we now know how much is attributable to level 2 versus level 1. So in this next slide, this illustrates how you would calculate that. So this is the output that we saw before. We just take those variances from level 2 and level 1, we add them together to get total variance, and then we take that level 2 variance and we divide it by that total variance. So we can see from this that 61% of the total variance in LF is attributable to between person differences. And of course, total variance in this case is going to sum to, the proportions will sum to 1. So we can say 39% of the variance in LF is attributable to within person variability. Now, in all honesty, this may be the most important thing that you learned today, because up until this point, if you were ignoring potential clustering structures, you had no way of knowing how much of your total variance was attributable to between cluster differences. So that is why this is important, because now you are partitioning that variance and recognizing the hierarchical structure of your data. Are there any questions about that?
So Paul, I might have gotten like a little bit lost in here, but right now you're just modeling your outcome variables with like the only things that are in this model are these two things of who it is and like what treatment I guess they had, or like which observation it was. You're not having like additional covariates in here.
There are no covariates. So when you look at this model statement, you'll see it's empty. And so SAS will by default include an intercept in there, and the intercept represents the mean. So at level 1, that mean represents each person has their own mean LF, but then what SAS shows you is the grand mean. So it just shows you, which is this, the gamma 0, 0. The grand mean is what we see in that output. So I'm gonna go back down. Oh, it's not in there. I'll go back to SAS real quick. So yeah, this is the grand mean. The intercept is grand mean. So the sample mean LF across all individuals and your data set. So yeah, we don't have anything in that model statement. And because it's a mixed model, it's also showing you these variance estimates for the random effects. And so we have 2 levels to our analysis. We have the cluster level, which is level 2, the person level. Level 1 refers to the lowest level of our analysis, which is those LF readings or diary entry readings. So you'll get those 2 variance estimates. So SAS will automatically produce that to you regardless of how many variables you have in your model.
Okay, so really right now what you're looking at is building a model as a means to tell you like how much variance is like attributed to which level. But then would this also get you the same to the conclusion of like effectiveness of one or like comparing, like doing hypothesis tests that way, like within each level?
So we're going to get to that next. Next, we're going to start adding predictors to our model.
Got it. Okay.
And we'll be able to see not only what's happening with those variables, are they significant? Are they contributing to LF? We'll also be able to see some changes, hopefully, in these random effects, these variances. And we'll discuss a little bit about what that means. So I'm going to switch back to the presentation.
Oh, sorry, you can say here, but right here, that p-value where you're saying like those are significant, all of that's saying is like there is a significant difference between levels, like between the observations within each level?
Yeah, so the top one is telling us that there is significant variance. There is significant variance in mean LF values
Mhm.
between individuals.
Mhm.
So that's what the top line tells you. The bottom line tells you is that those LF readings differ significantly within a person. So there's significant variance. We can't just assume that all those LF readings within a person are essentially the same.
Right, right. Okay.
And really what justifies the multi-level modeling approach is right here, where we do see that there's significant variance at level 2. If we
Yeah.
didn't have significant variance at level 2, meaning that there are no between person differences, then we could basically kind of say, like, you know what? There's no real clustering effect. These observations are independent from one another within a person.
Mm. Okay, that makes sense. That makes sense. Thank you.
Yeah, of course. All right. So I got to keep shifting everyone's faces around so that I can see what I'm doing. So now we're going to get into the actual modeling just beyond the partitioning the variance. So in its most basic form, most any MLM model that you'll run will be what's known as a random intercepts model. And we kind of covered that a bit because what we said is that we're letting that intercept vary. We're going to estimate an intercept for each person in our data set. Now, of course, our outcome variable is always going to be a level 1 variable. So if you're using MLM, your outcome variable is always going to be measured at level 1. Our intercept has this I subscript, which tells us that it's not fixed. It varies over everyone in the sample. So each person has their own intercept. So if it's not fixed, it's random. And then for the beta 1 through beta 5 effects, you can see that we don't have error terms. So looking down here, we don't have error terms. And that's because we're going to assume that these effects of these variables are fixed. They're the same for every person in the data set. So you can see we have age in here. We have these various activity levels, run, walk, stand. So this means that sitting or lying down is the reference value. So these are dummy coded. And then we have negative affect level. So simple model with just these variables in it. We're going to go to SAS to see what that looks like in proc mixed. I got to move these faces around again. All right. So here's our random intercepts model. It looks just like our null model, except now we have predictors in there. And so what you're going to notice is we have level 2 predictors, age, or level 2 predictor, age, and we have level 1 predictors, activity level and negative affect. You don't have to tell SAS which level these variables belong to. SAS can detect that in our data set. It can detect that age is the same within an ID level. It can also detect that activity and negative affect, that varies with an ID level. So that kind of calls back to your question earlier too about these different variables. So SAS will automatically recognize whether it's a level 1 predictor versus a level 2 predictor. So I'm going to go ahead and run this model. We're going to get a lot of the same information. So all this stuff that we can pay minimal attention to. Here's where we get to the random effects. So again, these are variances associated with those level 1 and level 2 error terms. So the error variance for level 2, the ID level, still significant. The level 1 error variance, still significant, but you may notice something. I'm going to scroll up back up to that null model. This is 254 and 162. When we scroll down to this one, this is 204 and 146. So these decreased a bit. And what that is telling us is that by adding variables, predictors into our model, we're explaining some of that variance. That's why these are smaller now. So just something to note. Now this technique is not foolproof, meaning that there are cases when I add variables that may not meaningfully contribute, they may be non-significant to our model, where these actually increase. So we can't really reliably count on these as an index of what our variables are doing. So now we have these fixed effects that tell us what's going on. So we have intercept, still have an intercept, but it's less meaningful now because we have these predictors. So we can see the age is negatively associated with LF. That's a pretty common finding in the literature. As you get older, your HRV levels tend to drop. Activity level, we can see that the more active people are, the lower their HRV. Remember, HRV is inversely related to heart rate. So that's like saying that the higher the activity level, the higher their heart rate. So that is exactly what we'd expect. And then here's what we are really looking for. We're looking for negative affect. And we wanted to know if it was associated with LF HRV. And we find this negative effect. So this is supporting our hypothesis that negative affect would be associated with HRV. And these are these default type 3 effects that I mentioned that SAS gives you. If you don't put in that /S, you won't get these effects. So this is a random intercepts model because the only random effect we have in here are the intercepts. So the intercepts are the only thing that we're allowing to vary from person to person. We can go a step further and we can actually model random intercepts and slopes. So here we can see that for negative affect, we've added in, oh, I'm sorry, I'm seeing raised hands. Do you want to go ahead and ask your questions?
I think I was first. So I just like to ask about something that kind of surprised me was in adding more fixed effects to this model, you don't essentially guarantee, even if it's trivial, like a decrease in unexplained variance. So that, I mean, that's a good sign. Does that hold true for random effects, or kind of just safeguards against like throwing whatever you can to get variance down?
Yeah, so we're going to see here what happens when we add random effects and some of the rationale for adding random effects. So kind of the interpretation of what's going on with those random effects if you add more random effects. We'll get to that in a moment. That's different from fixed effects. I know in kind of the statistics that we see in the social sciences and health sciences, this is not machine learning. We're not developing predictive models. We're developing explanatory models. So we may say, you know what, we have this clinical study. Gender may not have a significant effect in this model, but we have to control for it because we don't want that to be contributing to differences in our treatment effects, even if they're small. So in a lot of times you a priori identify covariates or control variables that you put in the model. So that's the case when you get into adding variables and you say, what's going on? My random variances are increasing when I add predictors.
Makes sense. Thanks.
Yeah. All right, Dan.
Hey, I just had 2 questions. Hopefully they're quick. And you may have mentioned this. I was grabbing food. So if you've mentioned this, then we can move on. But I was just thinking, like, how many patient, like, you're doing like intercepts per person. How many people do you need to have like a statistically significant intercept? If I'm even thinking about that right, like obviously if they have like 1 data point, I wouldn't want to maybe use that.
That's right. If you have 1 data point per person, then you just have a single level model. Typically, a rule of thumb that I go by is that if you have multi-level data, like you should have at least 3 observations per person or per cluster. And this will allow you to get reliable estimates of the intercept. Now, you can the grand intercept, when we get the fixed effects, that can still be significant even if you have a very low number of observations per cluster, because that's going to be based on the grand mean. Where you may see lower significance is if you have very few observations per person when you're looking at those covariance estimates, what's called the covariance parameter estimates, which are the random effects. And so that's where it's referring to level 1 variability versus level 2 variance. And so if you have very few observations per person, then it's possible that you're not going to see a significant level 1 variance, within person variance. But it really depends on what these observations are. I mean, or, if they're really meaningful, if you're measuring follow-up 6, 12, 18 months out, then these are probably going to be pretty different if you have like a, efficacious treatment. But if it's just like, I'm going to get heart rate every second or every 5 seconds, there's probably not going to be a lot of variability within person. So it really depends on the type of data that you're working with in that regard. Now, you may also be encouraging upon questions about like, what are sample size rules of thumb with this question. Again, typically, I like to have at least 3 observations per person. There are special case scenarios when you may only, or per cluster, I should say. There are special case scenarios when you only have 2 observations. Like there's what's called a dyad analysis. Like this gets used in social science research a lot, where you may be looking at married couples or parent-child dyads, where you only have 2 individuals per cluster, the cluster representing the dyad. And so when you have those special case scenarios, you can set a covariance structure that kind of accommodates those fewer observations. There's like a ton of literature on the special case scenarios. But again, 3 observations per person. And then when you get to level 2, like the number of clusters you have, it's kind of like any kind of regression. Like there's like different rules of thumb. Like it may be 50 observations plus 1 per predictor variable, or maybe 10 observations for every predictor variable. That's typically going to be the same with multi-level modeling. The difference is that multi-level modeling often has more power, more statistical power, so that if you have, say, 100 people with 3 observations each, and you were interested in, say, these observations were blood pressure readings, and you want to know if some treatment is leading to decreased blood pressure readings. If you take those 3 blood pressure readings per person rather than just 1 blood pressure reading, you're going to have more statistical power in that multi-level model with 3 observations than you're going to have with just a single observation, just running a t-test. There is an appendix that demonstrates that. Maybe I can go over it if it's something that's interesting to you.
Okay. Thankful. That's really helpful. And yeah, I guess my second thing, which maybe we don't have time for, I was just going to say, this looks like so powerful. I'm just like, why not throw this at every problem? But maybe you'll get into why we shouldn't do that.
Yeah. So, I mean, again, a lot of it, some of it's theory, like, should I look at these different clusters? Like, are these potential clustering effects that I would observe? You can put a null model in, and if you get a level 2 variance that's null, it's not significant, or even, in academia, we use a cutoff of 0.2, so not even like 0.05 or 0.01. And we say, if it's lower than 0.2, we're going to go ahead and model that random effect, that clustering effect, using a multi-level model versus running this as a traditional ordinary least squares regression. So, you can end up using this a lot more in situations where you may not have beforehand. That's certainly what I have ended up finding, because there are clustering effects in many places where you didn't think to look at them before. Now, when we look at this random slope that we just added in, this is the equation for it. Again, all I'm doing is adding in this error term and putting this little I subscript to demonstrate that I'm going to let this slope vary. We're going to go to SAS. I'm not going to go there yet, apparently. We're going to go to SAS and run that, and you're going to see an example of, oh, you know what? We didn't need that. So here's our random intercepts and slopes model. Looks the same as this random intercepts model. All I did was add in the slope in this random statement right here. I just put neg f right there after intercept. I'm going to run this model. And given that I've already run this before, here are our fixed effects, but I'm going to scroll up to the random effects. And so our random effects, before we were just seeing this top line here, which refers to between person differences in our outcome variable LF, and within person variability in our outcome variable LF. Now we have two additional lines, and I'll tell you why they're two and not just one for the random slopes. So this is using like matrix nomenclature. This is 1, 1, 2, 1. Our random slope is represented by this line, 2, 2. So however many random slopes you have, it's always going to be the same number. It's going to be one number, comma, followed by the same number. So it could be 3, 3, 4, 4. They're always going to be the same number designating that random slope. So here we just have one random slope. So it's 2, 2. We can see it's 0. So this means there's 0 variability in this slope across individuals in our sample. So here it's telling us you don't want to run a random intercepts and slopes model because there are no random slopes. Like this effect is essentially the same across all individuals in your sample. And it may be 0 because we don't have enough observations. We only have about 15 observations per person on average. Maybe we need more data to be able to more robustly estimate these slopes. But for the data set that we have, this is 0. So this is telling us there's 0 variability in those slopes and the association of negative affect with low frequency HRV across individuals in our sample. That's what the random slope is telling us. If this were significant, we may say, you know what, we should probably model those as varying across members of our sample. But it's 0, so that's telling us you can drop it. This is something that is provided when you use this type equals unstructured covariance method. This represents the covariance between intercepts and slopes. So when we have random intercepts and slopes, we're saying for every individual in our sample, we're going to estimate an intercept and we're going to estimate a slope. This is the covariance between those intercepts and slopes. And we can see that's negative and it's significant. All that's telling us is that there is an association between intercepts, so mean LF level for a given person, and slope, so mean change in LF associated with negative affect. And it's negative. So I'm going to try to apply some logic here. If you have a higher intercept level, a higher mean low frequency HRV level, then the association between negative affect and LF level is going to be lower for you than it is for people with a higher intercept level. That's what that covariance is telling us. And that may be a lot to absorb, so I will pause a moment for any questions there. And again, I will note that if you use different covariance structures, you won't see this covariance estimate. You won't see it because SAS is not making any assumptions about that. SAS is only going to be making assumptions about how your data, I guess how those observations kind of line up with one another across individuals in the sample. So you'll only get a random slopes intercept. So for instance, I'll go ahead and do that now. I'll put in what's called an autoregressive covariance structure. And basically what this is assuming is that one observation is going to be more closely related to adjacent observations of LF than observations that are more distally related in time or across observations. Does that make sense? So adjacent observations of LF are going to be closer to one another than ones further apart. I would say it doesn't necessarily hold here because these observations were probably on average a few hours apart. So I'm not really expecting there to be much correspondence at all, but I'm just using a different covariance structure just so you can see that. So here, ran the model again. Gonna scroll up and here we can see we're only getting this estimation for slope and this is blank, which is pretty puzzling. So an estimate of 1 and a standard error of 0. So I am guessing that this means that this covariance structure is not particularly appropriate for this particular analysis. And I'm going to tell you right now, you encounter a lot of errors when you run proc mixed, and there's a lot of documentation out there for why you might be encountering those errors. So you can go down a rabbit hole if you're not certain about how you want to specify these different estimates. Again, I prefer using type un because I don't want to make any assumptions about how these observations line up with one another. All right, so we've run the random slopes model, random intercept and slopes model. We found that those slopes don't vary across individuals in our sample. So there's not much that we don't want to model those. We'll take those out of our model. We'll get rid of that. We don't need that because this model suffices. And this is just the random intercepts model. Let me ask you this. What would happen if we wanted to model random slopes for age? Does anyone have any thoughts about what we might see there? Anyone? Okay. Well, let's put it in here and see. Age is 0. So why would age have age in its association with LF be 0? So I'll tell you, no one's chiming in with an answer. When you are modeling random slopes, the slope has to be the association between a level 1 variable with your outcome variable, which is always level 1. So I'll repeat, age is a level 2 variable. It doesn't vary within a person. So there's not going to be a within person association of age with LF. So you can only do this random slopes with level 1 variables. All right, wow, it's almost 1. So I'm going to pause here for any questions. If not, I do have a little more I can show you. All right, not seeing any questions. So I'm going to push on and show you one last thing before we go. So one of the issues with modeling level 1 variables is that we do not know what is necessarily behind that level 1 effect if it's significant. So we demonstrated that negative affect is associated with low frequency HRV, but it could indicate one of two things. It could indicate that when someone experiences greater levels of negative mood, that they're experiencing low frequency HRV. But we could also be telling us that people who have overall greater levels of negative affect have overall lower HRV. So we have to disentangle the level 1 and level 2 components. And the way that we do that is through grand mean standardizing and cluster mean standardizing raw scores. Grand mean means standardizing scores so that each person has a score relevant to the sample. Cluster means that each score within a person is relevant to their other scores that they had. So I'm going to show you the SAS code real quick. It kind of gets at the logic of why you do this. So here, we're going to calculate individual means and standard deviations, and then we're going to do the same with grand means and grand standard deviations. I'm going to go ahead and close these. So we'll run this real quick. We'll look at our output or the resulting data set, these I means, which are individual means. So now we see that for each person, we have a mean LF level and the standard deviation of the LF level. Now we're going to get the grand means that are going to be based on these means. So we calculate the sample mean and the sample standard deviation. We just have one because this is for the entire sample. I'm going to merge these into the data set that we already have, which I'm now going to call merged. And so now you'll see that this is the data set we started out with. Now each individual has an individual mean. It's invariant across people, or it's invariant within a person, but it does change from person to person, and a standard deviation. Now we also have a grand mean, and this is going to be the same across every observation and person in our sample. And with these, we can calculate the individual mean standardized scores and grand mean standardized scores. So individual mean standardized is just the raw score minus the individual mean divided by individual standard deviation. Grand mean is just that individual mean standardized score minus the grand mean divided by the grand standard deviation. The reason we do this is this provides two sets of scores. Individual mean standardized, grand mean standardized. These are actually unrelated to one another now because everyone has an individual mean standardized score where they have a mean of 0 and a standard deviation of 1. So if I put these into a correlation, I would see that these are going to be unrelated to one another. So now I can put these both in the same model and I don't have to worry about them knocking each other out due to collinearity. See that correlation of 0? So if I run this model, this is the last one I'll run. Now we differentiated, we disentangled between level 2 effects of negative affect and level 1 effects of negative affect. And so we can see that they both contribute, although this is what we would call marginally significant in academia. So not necessarily a significant effect. Really, that effect may be driven more by individual mean standardized score. So that within person effect of negative affect is driving that association with low frequency scores. So I realize we hit 102. You guys have been very patient with me. I appreciate you sticking around for this. Again, I posted a lot of materials on Google Drive, and there are a whole lot of appendices that get into different topics associated with multi-level modeling. Of course, if you have any questions about multi-level modeling, feel free to email me or find me on LinkedIn. Give me a reason to log in, and I will be happy to address your questions. So here are the various appendices. Of course, you can do this in R, Python. This is a method that's been around for many years. All right, well.
Thank you so much. That was great. And thanks to everybody for joining us today. We will share the recording of this session on our LinkedIn, or no, sorry, not LinkedIn, on our YouTube channel. And I will also be reaching out to everyone who has attended any of these webinars this year to find out what topics you might like to have us address in future Exploring Data Science webinars. And if any of you all might be interested in presenting and becoming as awesome as Paul here, then I'll certainly be open to self-nominations for future webinars. So thank you all. Have a great rest of your day.
Thanks, everyone. And thank you, Valerie.
Thanks.
Thanks, Paul.
Thank you.
Yeah, thank you, Paul.
Absolutely.
Are you staying on for questions? I don't want to hold Val up if you are hosting this.
Oh, I'm happy to.
I'll just hang.
Oh, you're muted, Val.
Okay. Paul, this is so perfectly timed because I'm working on something that I think this is just going to solve a lot of the problems. And I think I just need to maybe go through your slide deck a little bit slower